Okay, we have done with Tj just now. So we found that Tj equal to PD R thermal from junction to case plus Tc. So this is number 1 equation. Okay. So next, what about Tc just now? It's not Tj. What about Tc? So Tc is the same, and Tc is the same, which is the amount of PD that comes into the circuit for the same amount of current there, times R thermal across Cs plus the values of Ts here, Ts. So this is the second equation. Same goes to Ts. At this moment, Ts equal to PD R thermal SA from source to from heat sink to ambient plus TA. So this is 3. Then to conclude the overall circuit, what you have to do is that you put 3 into 2, then together 2 into 1. So the overall Tj now is equal to PD of number 2 here, PD of R thermal Cs, plus Ts, R thermal Ts plus, R thermal, what's upper here, R thermal Jc, okay, Jc plus Tc, but now Tc is PD R thermal Cs plus our Ts now become PD R thermal Sa plus T ambient, plus T ambient Okay, so you take out PD, remains as R thermal Jc plus R thermal Cs plus R thermal Sa plus Ta. This is your case here. So this is the overall Tg equation, which involve R thermal Jc, R thermal Cs, R thermal Sa, and with T ambient. So this is the equilibrium equation for circuit with heatsink device you attach to the heatsink. So you have your device with 3 legs here, you have your metal tap, you have your washer, not washer actually your what's it called, insulator, then you have your heatsink. So this is your heatsink, here. Between heatsink and metal tap they will put some sort like the paste, thermal paste. So thermal paste, they have their own material, thermal resistant, and at the back of the black plastic encapsule your dies, silicone oxide dies, they have metal tap. This metal tap will be attached to the heatsink through this thermal layer or thermal paste, and also the metal tap will attach to your plastic case here. So this is the element that represent between junction to case, between case to heatsink, between your tap into heatsink, between heatsink into ambient. So we have 3 elements here. 1, 2, 3. So 3 elements. That's what we have here. 3 elements of thermal resistance. Okay, got it or not? So it's end up with this is what's called equilibrium equation. Okay, let's say that if you have your transistor is attached to the tap, metal tap, but between your heatsink and your transistor tap, they just solder it, solder. It does not attach with any thermal paste, but solder, direct solder. So it means that from junction to case, the thermal resistance value provided by the MSDS of your transistor, and MSDS of your transistor, let's say MOSFET MSDS. So between your case into your heatsink, now it was soldered up, so becomes zero. Zero. There's no resistance because it firmly contact with solder. So no values. So 0 degrees C per watt. Meanwhile, your heatsink, the heatsink itself is provided by MSDS of the heatsink manufacturer. Okay, heatsink manufacturer. So each of your product or materials here, the characteristic is provided by their own or individual manufacturer. But if the device is directly firmly sealed or soldered to the body of your MOSFET, between MOSFET and heatsink, so the resistance considered as 0. But if you use solder paste or solder insulator, heat paste, thermal paste or thermal insulator, maybe you can see that the value between 0.1, which is best, or up to 0.5 or 0.8 like that. Okay. But if it is directly soldered, so the value is considered as 0. Okay, we move on to the next slide of the lecture note. You can see that this is the example that we used to see, or example that we used to discuss inside our lecture. You see, this is the source. When on the positive cycle or positive pole, the current will flow into your diode. Okay, please remember that we have learned on the switch kind of switch type that available in our power converter, which is so-called. So we have learned that we have what's so-called uncontrolled device. Uncontrolled. Another one is semi-controlled. Semi-controlled. Another one is fully controlled. Okay, fully controlled. So what is uncontrolled? So this is uncontrolled. Means that when the current pass forward, when we have a forward bias, it will switch on or it will conduct. But during the reverse bias, so it will be blocked. So this is uncontrolled. You cannot control. Another one is semi-controlled, whereby we have a SCR. Over here we have the terminal to put a signal, terminal to induce a signal. So it means that during forward bias, you have learned before, during forward bias, and at the same time we have signal being applied to the terminal here. So what happens that during positive bias, it will conduct, but during negative bias, it will be blocked. But the positive bias, other than you have positive bias, you have to apply your signal. Means that during positive bias, maybe you apply your signal over here, so it will conduct just at this point. So the result will be some sort like this. And so it just conduct over here. If you trigger here, so the conduction will start here. If you trigger here, the conduction will only start here. So this is called a semi-control. You can control in terms of where to switch on, but it will switch off based on the reverse bias of the current. Once reverse, it will cut off. It will start only during your alpha triggering. Okay, this is so-called semi-control. Another one is fully controlled, which refer to MOSFET, IGBT, GTO, like that. is that if you put your signal, so it will follow. If you take out your signal, so it will switch off. And you give signal, it will start to conduct. You take out the signal, it will stop to conduct. So this is fully controlled compared to semi-controlled, compared to uncontrolled. So now we look at uncontrolled device. So for this uncontrolled device, during positive cycle, so it will conduct. Negative cycle, it will stop. Positive cycle, it will conduct. Negative cycle will stop. So what happens here, during positive cycle, the current will flow into your uncontrolled device, into your load, resistive load, into your inductive load, and back there. So what happens that when we focus on this power switch, you are not focusing on the load. Power switch, how much dissipated power here? PD is referred to dissipated power that consumed or wasted inside your switch. This is your switch, power switch, and we are concentrating on the power switch which consumes power during operation. So this is your PD. How much is the heat that generated at your junction during operation? Junction is just like your engine, your car engine. How much is produced inside your piston when you operate? And this heat need to be dispersed into your ambient. Need to be taken out into the environment, outside environment. And it has to go through your case, see the case, and go through your heatsink and then only your ambient. That's what we have here. During operation, the heat generated at junction need to pass through your case, throughout your heatsink, into your ambient. So this is the values provided by the heatsink manufacturer. This is the values parameter provided by the thermal insulator or thermal paste manufacturer, and this values is provided by the MSDS of your transistor manufacturer. So we have three reference of manufacturer here, and so you have to consider, because the one maybe comes from different manufacturer. This is from semiconductor device manufacturer. This one comes from mechanical factory. And the other one comes also from mechanical factory. This one is chemical. This one is mechanical. So three different fields. So you have to match all the three fields into your design actually. Okay, for single device, we just need single heatsink. So it's so-called a individual heatsink. You have one device, you attach to single heatsink. So this is single heatsink. But when you have some sort of this is a full bridge rectifier. It comes in module or it comes in individual thyristor. This is thyristor. We have triggering port here, thyristor. So this might be attached to one heatsink. You have 4 devices here, and you have 4 devices here. Might be attached to one heatsink only, and or you have individual heatsink for each of it. So it depends on the design and on the constraint of your module later. And if you want to design in a bigger space, maybe you can provide different heatsink, individual heatsink. But if you are confined or your space is limited, so you have to combine them all together. So it will involve different kind of consideration. So this is the representative of heatsink that being combined all together. And so you have different junction temperature, but you combine into one heatsink. And so you have all these components before it reach ambient. And each of your component part produce their own heat and their junction temperature. So from junction into your case, JC here, it has the thermal values. From case to heatsink, we have here. This one from case to ambient, and case to ambient. And usually from case to ambient, when we put a heatsink, so we consider that all the thermal will go into heatsink to ambient.